Good afternoon, everyone, and welcome to RTDology, Burns Engineering's online training series. I'm Jeff Wiggin, National Sales Manager at Burns Engineering, and presenting today will be Bill Bergquist, Senior Applications Engineer. Today's presentation, Surface versus Immersion Temperature Measurement, is the latest in our series of web-based training modules designed to help you better understand temperature measurement and achieve your measurement goals. If you've joined us for any of our previous sessions, we'd like to welcome you back. If this is your first time, welcome. And when you get a chance, please do check out our previous presentations on the RTDology page at burnsengineering.com. Before we get started, just a few housekeeping items. To respect everyone's time, we'll make every effort to limit the presentation and Q&A period to 1 hour. We highly encourage questions, so please type them into the Q&A section or the chat box on your screen and send them to host and presenter. We'll attempt to answer as many as time allows. Today's session will be recorded, and we will provide session notes and a link to the recording as soon as they're available. So don't worry if you miss something. Typically, this is probably about 2-3 days when we have the recording, and we'll get that out to you. If we don't get to your question or you need some additional assistance, there will be contact information provided at the end of the presentation. Please do contact us. We're more than happy to help you get an answer to your question. And finally, if our goal is to answer your temperature measurement questions and challenges, we've built RTDology around commonly asked questions and issues. However, if you have a particular topic or issue you'd like to have considered, give us a call and we'll see what we can put together for you. That covers the housekeeping. So without further delay, here is Bill Bergquist to discuss the ins and outs and the pros and cons of surface versus immersion temperature measurements. And just to give you a little bit of background on Bill, Bill's got 30 years of experience in the aerospace, industrial, and laboratory temperature measurement with RTDs and thermocouples in roles of design, sales, and management. And myself, I've been in the sales and marketing B2B world for custom design, made-to-order products in the industrial and biotech market for, I hate to say it, but almost 25 years now. So with that, take it away, Bill.
All right, thanks, Jeff. Well, today I wanted to address the difference between surface and immersion measurements. It's a question that I get quite frequently, and I wanted to throw out some of the pros and cons of using a surface mount RTD or thermocouple versus something that's immersed directly into the process. So we're going to go through and look at the surface and immersion and how they are placed in the process, and then how we protect them, and then we'll end up looking at performance and finally price, and then what we can expect as a service life. So these kind of 5 main factors to consider here when we're doing any selection of any RTD or thermocouple or placement, protection, performance, price, and the service life. First off, there are kind of just in general 2 different ways to measure temperature with these 2 devices, and we can use a surface mount where it's strapped onto a outside of a pipe or a tank, or we can have an immersion style sensor such as these 2 where it might be directly immersed into the process, or using a separable thermal well such as this one. And these are just, we're just going to look at a few standard types of surface mount RTDs and thermocouples. These can actually be built usually with either measurement technology. This one is just an aluminum block. It's the sensing element is buried inside of it, and strap it to a pipe with a hose clamp. A device like this uses a nut that is welded to a surface, and the sensor screws into it, and the sensing element would be right at the very tip of this, what is essentially a bolt that threads into the nut in this location. And that'll give you a fairly accurate surface measurement. And with any of these, there are some performance issues that we'll talk about a little bit more. Here's another style that's held down with a couple of bolts. This type, again, with a connection head to protect the wiring. Might be in an outdoor application, for example. Here's a smaller surface mount sensor that is attached with silicone rubber. And there's also methods of just taking a small diameter sensor, wrap it on the surface of a pipe with some silicone rubber tape or fiberglass tape, whatever might work. Another style of surface mount sensor, and this one was intended for a small diameter tube, and it's held in place with a hose clamp that goes around the two ears right here. And heavier duty type uses a big pipe clamp design, and then if you look real carefully in here, you can see a little copper tipped, in this case it's an RTD, could also be a thermocouple, and it's spring loaded, and so that touches right on the surface of the pipe, and then we protect that with a connection head. Could mount a transmitter in it, indicator, whatever's convenient. Another style of, and I guess I'm going to classify these as surface mount sensors. They're not really a true immersion style, but the tip of the sensor actually does come into contact with the product. In the case of this sensor here, this sensing face, it's right in the very center is where the sensing element is. And this would mount into a bottom of a tank, for example, that may have a mixing blade in it where you can't have anything immersed in it. But we get a little more intimate contact with the process fluid by eliminating the tank wall, and the sensor actually becomes part of that wall. This design over here can work the same way with an NPT thread. The sensing element is right at this face, and the sensor can be screwed in so that face becomes flush or nearly flush with the interior of the pipe or vessel. Another hybrid style of surface mount sensor incorporates an insulated container that protects the sensing element from the ambient conditions. And we're going to talk a lot more about the effects of ambient conditions on the accuracy of the measurement. But this is a kind of an all-in-one solution here. It can be installed in a piping system with a, in this case it's a tri-clamp fitting. It can be welded in place, NPT threads, almost any kind of connection design you can think of. These sensors are available from various manufacturers. We can see here that the sensing element is bonded right to the inner tube, which matches your process tubing, and then it's insulated with some either ceramic fibers or other types of insulation. Wires run out, and that can be run into a cable extension, or in the case of the photo we show here, a connection head could be attached to it. And these work fairly well. They're nice in that they are all environmentally sealed, and with some types of surface mount sensors, environmental sealing can be a bit of an issue. Now, inside, one of the sensing element technologies that works really well for surface mount is the thin film sensor. And this is a highly magnified photo of one. We can see this one is 0.17 inches long, and you can see the little platinum trace right in this area here. And then the lead wires are connected to that platinum trace underneath this glass, this blue glass mixture here. So the reason these work really well is that they're very small, very low mass. You can attach those to a surface very easily. They do need to be protected very well, and as you can imagine, these lead wires back here, being very small, can be kind of fragile. So there's a lot of technology that goes into not only building the thin film sensing element, but really to get it packaged correctly so that it can survive some normal industrial vibration and other abuses that they go through. Those lead wires and the sensor need to be connected to the tubing correctly so that you do get that durability out of it. I threw together some installation tips for all the different types of surface mount sensors. One of the big things, as you can imagine, is getting a good thermal contact between the sensor and the surface that you're trying to measure. A thermally conductive paste really goes a long way towards getting you a much more accurate measurement. It speeds up the time response, but it also will minimize conduction errors. And anytime we have a surface mount sensor, they're very susceptible to the effects of the ambient conditions. And having more intimate contact between the sensor and that surface helps minimize those conduction errors. One of the biggest things you can do for improving the accuracy of a surface mount sensor is to insulate it. And this can be as simple as just a little fiberglass blanket put over the top of it, and it helps to shield the sensor from the ambient conditions, whether it's just a temperature differential from what you're trying to measure inside of the pipe or a tank, or it might be from radiation. If it's outdoors, it might be sunlight. Indoors, it could be maybe a heater or a fan blowing, those kinds of things. As you can see from our little test that we did, we can improve the measurement by up to 70%, which is a really big number. And I did mention that some of these designs need to be protected from especially liquid water. Most of them are sealed up very well from just humidity that might be in the air. But liquid water is usually a little bit of a different story. It can go and seep its way past an epoxy seal that might be in a sensor. And you really need to further protect that sensor from liquid water. So if we look at some of the pros for surface mounts, they're very easy to install. You don't have to cut up your piping or the tank or anything. Just slap it on the outside, insulate it, and there you go. Works real well for small diameter lines where you don't want to obstruct the flow, and most of these are very low cost. They do need insulation of some type, and if it's an outdoor application, you need to use some type of waterproof insulation or put some kind of a shelter over it to keep it dry. Then when it comes to maintenance, because of the configuration of a lot of these parts, they really don't lend themselves to being placed into a hot block. Most of them are going to need some kind of an oil bath or an ice bath that you have that you can fit some of these odd shapes into to be able to calibrate them. Most hot blocks are just going to have some cylindrical holes in them, and some of the pipe mount sensors and things, they just don't work with those types of calibration equipment. So that's one thing that you really need to take into consideration if you're going to use some of these sensors, is that maintenance aspect. And then when it comes down to the measurement accuracy, we're measuring the pipe surface. We're really not measuring the fluid inside. In the case where you want to know that temperature, there are a lot of instances where we are actually looking for the temperature of a particular surface. One of the examples I can think of there is with machining castings. And if you need really tight tolerances on machinings that you're doing to a casting, you need to know the temperature of the casting so that you don't go just because of the expansion and contraction of that casting when it gets up to its operating temperature in the machine that it's going into. You need to start out at maybe a little different tolerance to be able to hit the final tolerance for that part. And doing some kind of a surface temperature measurement will enable you to better hit those tolerances. Some of the other applications for surface mount would be for bearing temperatures, where we're just interested in maybe the monitoring the outer race of the bearing. Might go into a pillow block, or if there's an oil bath that surrounds it, we might be monitoring the temperature of that outside of that pillow block. Again, small diameter lines work real well. And then also for tube skin heat exchangers, and I see a little diagram here got a little messed up somehow. But anyway, this would be the little weld pad that would get welded onto the tube. And these are typically used with thermocouples. They get a real fast time response and real intimate contact with the tube that you're trying to measure. Exhaust temperature, very common application for a surface mount sensor. And then we get into viscous or corrosive fluids. Sometimes these are they're either too sticky or just too corrosive or erosive to put in an immersion style sensor. The material would build up on the sensor, maybe even eventually block the piping if it's really bad. So surface mount sensors would be a good application for those kinds of measurements. Now, I don't know if we have any questions yet, Jeff. We can just kind of jump in here. If not, I can just plow ahead here.
Well, there was one question, and I don't know if you're going to hit on it in the coming up here or not, Bill, but just this question in regards to accuracy, and you sometimes hear about 3-wire versus 4-wire and Class A versus Class B, and just wondering, if you're working with a surface sensor that may not be quite as accurate to begin with, do you really have to concern yourself with a 4-wire versus a 3-wire, or going to a Class A versus Class B?
There are two error sources, and the sensor part of it is certainly one of them. And it doesn't hurt to start out with the most accurate sensor that you can get. The biggest errors, though, with most surface mount sensors come from the installation and the ambient conditions affecting it. But if you can, mediate those kinds of error sources, it really is a good idea to go to the most accurate sensor design. You might want to consider a 4-wire sensor if you have a long lead wire run over to your control system or a transmitter. That's going to eliminate that lead wire error that you may end up with in a 3-wire system. So those are just some considerations, and I always like to go more accurate because it's you're going to end up with a better product quality, plus make better use of your energy dollars.
Okay, and then we've got another question. You had kind of touched on the thin film sensing element that's often used in surface sensors. And there's just a question: are wire wound elements, are those used in surface sensors as well? And when would you use one versus the other? A lot of it would depend on the type of measurement you're trying to make. The thin film works well if you're looking for the fastest response time from an RTD. The wire wound version is going to give you a more stable, repeatable measurement over a long period of time than a thin film will. It's a very small difference in relation to the kind of accuracy that a lot of people want to get out of a surface mount sensor. But it certainly is a bit of a consideration. Okay, thanks.
So moving along to the immersion style sensors and how they compare. When we look at these, we have what we call a direct immersion, which would be a sensor where the sensing element is potted right into a metal thermal well of some kind. And then there's the indirect version where we have a separable thermal well and a sensor that you can take in and out of it. With either of these, some of the considerations that you need to look at are wake frequency and strength, because if we have a real high flow rate, any of these designs can start to vibrate and cause a failure of the sensing element, or even the thermal well or the direct immersion style sensor. So when we put an immersion sensor into a piping, we're going to get a lot faster time response than we do with the surface mount. We've got roughly 4 seconds versus 26 seconds for a surface mount sensor. These are still fairly low cost. You do need to cut a hole in your pipe or tank and install it that way. We can get by with a fairly short immersion length though. And these are typically going to be much more accurate than a surface mount sensor because we've eliminated the air source of the ambient conditions affecting the measurement. And some of the limitations that we might see here would just be with durability and strength. And then finally, maintenance. If the thing needs to be replaced or calibrated, you do have to open up the system and pull it out. You might have to, drain fluid out of the piping or whatever it might be and pull it out. So that can be a bit of a disadvantage. The addition of a thermal well, though, makes that maintenance issue go away. When we look at one of the bigger error sources here for either of these immersion style sensors, it's what we call stem conduction. Sometimes you'll see it referred to as immersion error. And what's happening is that we have a difference in temperature between the product we're trying to measure and the ambient conditions. And the heat wants to flow from an area of high temp to low temp, back and forth. And so you're going to get some conduction along the metal parts, well, any components of the temperature measurement sensor, whether it's the thermal well or even the lead wires. There's a little bit of conduction that happens along those, and it does affect the temperature measurement. And you can see one of the ways that we can help eliminate that is to make sure that we have sufficient immersion length to overcome those errors. And in the case of a surface mount sensor, we can control some of this errors due to radiation and conduction by adding insulation over the top of the sensor. Outdoor applications, we have sunlight to be concerned with. The wind is blowing. The even rainfall getting on top of an uninsulated, unprotected sensor can actually cause a bit of a cooling effect. You have some of that evaporative cooling, and that's going to increase that conduction error effect. A little test that we put together here used an immersion style sensor with a separable thermal well, so it's an indirect immersion style. And the sensor was slowly lowered into 3 different baths. One was at 0, 100, and then 200 degrees C. And the error is actually expressed as a percent of delta T. So it's a percentage of the difference between the bath temperature and the ambient conditions. This is the 0 point right here, so this would be the line of 0 error. As we can see, we get out here to about 2.5, maybe 3 inches of immersion before we really start coming down to an error that's getting more difficult to measure. By the time we get up here to about 4.5 or 5 inches, can't really detect any error from stem conduction. And this test was performed in the laboratory. We did not have, sunlight blasting on it or a fan blowing on it. But that gives you some idea of how much of an effect that those ambient conditions can have on an accurate measurement. Some of the other ways to overcome this immersion effect, like if you can't use a surface mount sensor because you need better accuracy and you need to put a direct immersion sensor into a small diameter line, placing it into a T like this is a real good way to accomplish that. There are some other methods where a little different style T fittings that can work well also. The addition of a thermal well can also be used in a T fitting like that. So if you need to keep the system closed, we can put a thermal well in. And you do get the additional durability. It helps protect the sensor better. High flow rates or viscous products, you get extra strength from that. Plus it makes your maintenance a lot easier. You can pull the sensor out, recalibrate it, or if it has failed or if it's just time for a replacement, you can easily swap that out. You know, it does slow down the response time, and again, you need to get, ideally, with this type of well anyway, about 4.5 inches of immersion to maintain the best, most accurate measurement. One of the more important parts of selecting an immersion style sensor is taking into consideration the wake frequency and strength limitations. And here, this is a graph. It's from an older version of the standard, but I just throw it on here because it just shows that how important this really is. If we have a 1/4 inch diameter sensor, and it's here it's a 4-inch immersion, our maximum safe flow velocity due to, in this case, it's going to be wake frequency, is going to be about maybe 30 or 40 feet per second. And if we add that thermal well to this, similar to the one that we just showed, we're well over 200 feet per second. So it does make quite a big difference. And as you increase the length of the sensor, the maximum safe flow velocity is going to decrease. You know, and I've seen, you know, more than one failure from a sensor being put into you know, even a tank, but especially in piping systems, and the flow is just too fast for that sensor, and if the as the flow is going by a cylindrical object, it'll start to have what they call vortex shedding, and these vortices oscillate at a certain frequency, and if that frequency matches the resonant frequency of the sensor, it'll start to vibrate. And it can only handle so much of that before the sensing element fails or the sensor actually breaks off. And I've seen both of those things happen for systems that were not designed correctly. Put in too long of an immersion sensor in, or it wasn't, typically just make it a larger diameter to make it stronger and avoid that resonant frequency issue. That's a really important concept, and it's always something that you want to inquire about when selecting an immersion style sensor. And again, you know, for the surface mount sensors, really not much of an issue. Moving on to how we look at some of the ways to protect the outside of these sensors. Most of the immersion style sensors lend themselves real well to being protected with connection heads and other things. Surface mount, not so much. I also wanted to look at some of the hazardous atmosphere measurements and how we might go about doing that with a surface mount sensor. With the immersion styles, it's you know, very simple. We can put a connection head on it. We can attach our lead wires. Protects the sensor from all the nasty ambient conditions. We can, you know, use explosion-proof housing, stainless steel, plastic, aluminum, whole variety of things to choose from there. They also work real well for installing a transmitter or a local indicator for the temperature measurement. Again, a lot of the immersion sensors do have approvals for hazardous atmospheres. And one thing is that you will not find many surface mount sensors that have an FM, CSA, or ATEX ratings for hazardous environments. Now, one of the ways around that is to use an immersion style sensor that as shown here. Put a little dog leg bend in it and strap it to the, in this case, a pipe with a couple of hose clamps, insulate it, and there you have your FM or CSA approved temperature measurement system, and it can go in a hazardous environment. So there's always more than one way to use an immersion style sensor, and this one has shown that it works fairly well. Some of the other options for immersion style sensors, just to make maintenance a little easier, would be the addition of a pipe union. It makes removal of the sensor from a thermal well much easier. You don't have to disconnect any of the wires inside the terminal head. Just undo the union, pull it out of the well, and then you can just put it right into a calibration block, for example. I'd already mentioned the union here. It does make a real simple way to pull things apart and take care of maintenance. And also, it allows you to spin that connection head around so that you can line up your conduit with the conduit port on the connection head. Now, the last thing I want to talk about today was performance and how we can overcome some of these error sources that are inherent with surface mount and also with some of the immersion style sensors. We look at kind of two basic categories here. I look at the sensor accuracy, and then we actually have the measurement accuracy, which includes the installation errors, time response, which can be related also to the sensor performance, but mostly it's how the sensor is installed in the process. There's error sources associated with the control system, or maybe a chart recorder, transmitter, and again, immersion sensors usually more accurate than your surface mount sensors. One thing with both of these type sensors, RTDs do drift over time. Thermocouples are going to drift a little bit more than what RTDs do. This graph is for an RTD. And as you can see, down where I guess probably a lot of temperature measurements are made, drift with an RTD is really pretty minimal. As you go up in temperature, it does increase quite dramatically. And I guess the same would hold true for thermocouples. At the higher temperatures, they are going to tend to drift faster than at temperatures closer to ambient conditions. And I said earlier that I always like to choose the most accurate temperature sensor that we can get because energy is expensive, and just a degree or two off can end up causing a pretty significant hit to the budget for if we look at over a year's time. Time response can be one really big error source if your process is changing temperature rapidly. If we look here at a direct immersion style sensor, and that's this line right here, we can see that the as we immerse a sensor from one temperature into another, this is the amount of time it's taking for the sensor to register that temperature change. We can see that this direct immersion style sensor, this one happens to be 1/8 inch diameter, so it's real small. we get a real fast time response. And we can contrast that with an indirect style sensor like our thermal well sensor setup we had, and we can see how much slower this one is, and it goes way out here, well over 100 seconds before it even starts to approach, indicating 100% of that total temperature change. And all the other versions are in between here, like a surface mount. We can pick that out of here. It's right in this area here where it's still a little bit faster even than something like this, but it's still much slower than going with an immersion style, especially the direct immersion style sensor. Now, when we test time response, we'll do it by moving the sensor from a temperature bath of a known temperature into another, usually like well, we usually go from like an ice bath just because it's real convenient to start there with the sensor, cool it down to 0 degrees C, and then go into room temperature water that's moving at 3 feet per second. And the time constant, which is used as comparison for RTDs and thermocouples, is the amount of time that's required for that sensor to indicate 63.2% of the total change in temperature. So for example, if we were going from 0 to 100 degrees C, the time it would take for that sensor to go from 0 to 63.2 degrees is the time constant. And this would be the test that's done for immersion style sensors. Now for surface mount sensors, typically it's done a little bit differently. The numbers that I'm quoting here, the test was done with the sensor strapped to a stainless steel pipe, and it was we used 1 inch of insulation over the sensor, ran water through it at 3 feet per second, and so the pipe would start out filled with water at a certain temperature, and then water of a different temperature would be run through there. We monitor how long it takes for the surface mount sensor to indicate that change. And this has to heat up the pipe and everything, so we tried to simulate what a real world situation might be. Immersion sensors, we get about 2.5 to 8 seconds, and surface mount, really wide range here, anywhere from 10 to 70 seconds. And these numbers were highly dependent on whether or not a heat transfer paste was used and how the sensor was mounted, how well or how intimately in contact the sensor was with that pipe surface. Makes a huge difference.
So, Bill, we've got a few questions here. You kind of hit on the heat transfer paste again, and we got quite a few questions on the heat transfer paste. Is there a specific formulation or brand name that's often used, just in general?
Yeah, there's a few different types out there. The one that the one that I like uses it's a silicone oil-based paste that has a ceramic powder mixed in with it, and it's used a lot for like heat sinking integrated circuits on a circuit board. It's got a real wide temperature range, and you can put it on a surface and get it up to its max temperature, which I think is about 200 C, and it won't run or drip or do anything or separate out. I guess the only disadvantage with it might be, the temperature range. It is a bit limited. And then on the cold end, it does stay fluid for quite a while, down to, I think it's around minus 40 or 50 degrees C. I don't recall for sure, but it does work really well. Higher temperatures, there are some ceramic things that work well. And if you have a situation where you have a thermal well that's in like a vertical orientation, some sort of oil could be used. Maybe even like a antifreeze, like propylene glycol or ethylene glycol. Those are some things that have been used, and they work okay. There's not really any one definitive material. It really kind of depends on how you're going to use it, where it's going to go. I can think of situations in like maybe food, beverage, and maybe some pharmaceutical applications. You may not want to use any of that stuff in a sensor that might be immersed in the process, because if you did have a failure and that stuff gets into the system, it could be a real pain to get it all cleaned out. So, but for surface mount stuff, you probably have a little more variety of things that you can use there.
And one of the follow-up questions was just about are we aware of any heat transfer paste that's approved for clean room applications or pharmaceutical applications? And I think you kind of hit on that.
Yeah, none come to mind, and I don't know if you could get by with, if it's something that's not, in a sensor that's immersed into the process. If it's just on the outside of a pipe or tube or something, I'm not sure what all the requirements there are. But even a thermally conductive epoxy or silicone rubber does make a good heat transfer paste. So I would imagine in situations like that, that may be something that is suitable and would be approved. There are numerous types of silicone rubber, and they use different fillers in them. I know I was even at the auto parts store the other day, and they had the stuff that had some copper something or other in it for getting a little better heat transfer for attaching some component to an engine. I didn't really look at it all that carefully, but that may be a potential solution there also.
Yeah, we do see silicone oils used a fair amount if the application is in a vertical orientation, so it doesn't flow out. But when it comes to the pharmaceutical arena, most folks aren't real comfortable with putting one additional component in there. So we're typically looking at trying to find a different way to get good contact, and they're typically within a thermal well. So then it's just matching up the size of the sensor with the bore of the thermal well to make sure you get a good fit, and making sure that sensor sits down at the bottom of the thermal well. So that's some of the things that we're dealing with there.
All right. Well, so time constant is a real important thing to look at, and especially with the surface mount sensors. The other ways we can improve the accuracy of our measurement might be to add a transmitter into the measurement loop. And I've discussed this before, where we can actually calibrate the sensor. We actually end up characterizing its resistance at various temperatures. We use that information to adjust the transmitter so that we eliminate a lot of the manufacturer's interchangeability out of that sensor, and we're looking at just its most basic performance, which would be short-term repeatability, a little bit of drift, and the self-heating, and maybe some other small errors. So you can go from like a plus or minus 0.77 degrees C down to 0.11 degrees C by just matching the RTD to a transmitter. So it's a very economical way to improve the accuracy of a measurement. And in the case of thermocouples and even RTDs, if you're running that signal for a long distance, you do get a much more robust signal from the transmitter, less susceptible to radio frequency and electromagnetic interference. And finally here, we're just looking at the life cycle cost of the part. And usually, the initial cost of the sensor is usually one of the lowest, the least amount of money you're going to spend on that measurement point. When it comes to doing all of the maintenance, efficient use of energy, and if you buy a sensor that's not suited for that application, where maybe the durability wasn't there, maybe the wake frequency wasn't taken into consideration, you're going to have some reliability issues there, resulting in a lot of downtime and troubleshooting, potential product loss, keeping spares in inventory. So those are the kinds of things that need to go into that accounting equation for the total life cycle cost. And again, the initial cost of the sensor is usually the smallest amount of money that you're going to spend on that temperature measurement point. And again, just to repeat this again, it's just choose the right sensor and really look at all the different things that are going to affect that measurement accuracy, and then calibrate the instrument at regular intervals, just to make sure that it's working correctly. One of the other items to look at would be measuring the insulation resistance of that sensor along with the calibration check. Those things will help verify that you're maintaining a good accurate measurement for that point. I guess just to wrap it up here today, if we look at some of the biggest differences between the surface mounts, we've got really low cost, very easy to install. Do need to protect that sensor from the ambient conditions. Accuracy is, not the best, but in situations where you need a temperature measurement and you can't cut into the pipe or the tank or whatever it might be, it makes a real good solution. The immersion sensors will give you your best accuracy. You need to make sure that the immersion length is suitable for the size line that you're trying to measure in the sensor style, whether it's a direct immersion or an indirect immersion that uses a separable thermal well. And finally, the wake frequency and strength issues are also very important to look at to make sure that you don't have a situation where the sensor is going to fail due to vibration or just break off due to insufficient strength. And with that, I think we're going to move on to maybe some more questions here.
Yeah, thanks, Bill. Thank you very much for the presentation. Appreciate it. We do have a few minutes for questions. We have several questions pending here, so we'll start going through those. And then if you do have any other questions, go ahead and type them into the chat section, and we'll attempt to get you an answer. So one of the questions here from Bob is, what's the biggest seller of the three categories? And I think he's referring to surface, direct immersion, and indirect immersion.
Wow, that's a good question. That almost should come from the, I guess I always look at using an immersion style first because it does give you the most accurate measurement. And I'd have to say that that's probably the bulk of what, I guess it's a popularity contest. That's where the bulk of it would go, is right there with the immersion style. The surface mount does have some places where it works really well, and those are the real small diameter lines, and other situations where you just can't cut into the piping. But usually we strive for getting the most accurate measurement, and that's usually with an immersion style sensor.
Right. I think the answer is it all depends upon the application, specifically. But that's where it starts. If you can measure, if you can get the sensor into what the medium that you're trying to measure, that's the best. The next best is if for some reason that doesn't work, then you put it inside a thermal well, and then if that doesn't work, you go with a surface sensor. unless, of course, what you're trying to measure is the surface temperature, in which case you go with a surface mount. But so another question is, which style works best when you're measuring temperature in a steam flow? In other words, a steam in place application.
Yeah, this would actually be the direct immersion style sensor, and just as small a diameter sensor as the flow rate would allow. I've seen a lot of applications like that where an 1/8" diameter sensor with maybe 1 1/4" of immersion seems to work real well. And if you can get a little more immersion, that's even better. And putting it into a sanitary tea, for example, so you can get even more immersion, is another good solution. There are some what we call an elbow-style thermal well, where you can get that kind of sufficient immersion, plus there's no real dead lag associated with those. So that makes another good solution. But really, the direct immersion, real small diameter, works the best for measuring steam. Just because steam doesn't give up its temperature, it's not as conductive as liquids are. And moving to the next step there, just trying to measure air temperature, that's even slower yet. So really small, low mass type sensors work the best.
Okay, then another question here. At what length of the RTD or thermocouple lead wires would you recommend using a transducer for signal stability? Might be talking about a transmitter here.
Yeah, this would kind of depend a little bit on, in the case of an RTD, if it's a 3-wire or a 4-wire system. And then if in the case of a 3-wire, there is an error associated with 3-wire systems, and it amounts to about, 0.16 degrees Fahrenheit for every 100 feet of 18-gauge lead wire. And that's based off of a manufacturer's resistance tolerances for those lead wires, because in a 3-wire system, the accuracy of that lead compensation depends on each one of those conductors having exactly the same resistance. And of course, in the real world, they do not. So you're going to get a little bit of an error associated with that. So it really kind of depends on how accurate you want that measurement to be. And in a 4-wire system connected to a device that has a capability of doing a 4-wire lead compensation, you don't have to worry about the individual leads varying in resistance, because it compensates for all of it no matter what it is. The other aspect to look at there might be from the radio frequency and electromagnetic interference. Thermocouples are a lot more susceptible to that, so I always recommend putting a transmitter as close as you can to that thermocouple. And if you do need to get a distance away, that you use shielded cable and not run it near anything else. That's going to potentially cause some interference. So yeah, I guess that's about it. It's always better to go with the shortest leads as possible.
Okay. Now we've got a question from Al. Will or can the session with voiceover be posted on the website or available to reps? And the answer is yes. In fact, what we'll do after this session, it usually takes a couple of days, but what we'll do is send out a PDF that has notes from the session, and then also a link to this recording. So you can share that link with other folks as well if you want to pass it along. If there's people that weren't able to make it to the session, and they can view the whole session. And then I know if you get any more questions, go ahead and type them into the chat box. I know there was another question from Bob, and it was a pretty pretty specific question. So what do you see for the future in sensors, Bill? Just
so, well, yeah, there's a lot of different things.
I mean, what we're seeing right now, and there's, people are always looking for, hey, can I have a non-contact sensor? I want to be able to get a contact temperature with a non-contact sensor, and right now, that technology, there's some drawbacks to it, and it certainly is not as accurate or as cost effective as people would like. So for the foreseeable future, RTDs and thermocouples are going to be around. But what we see is smaller. A lot of folks going with smaller, looking for the same type of accuracy, same types of applications, just trying to put it in a little smaller package so that there's a little bit more room with all the measurements that are going on, really trying to maximize the space or minimize the space that's used. We also see in a lot of cases where they used to have one temperature measurement on a system or on a pipe, now they've got 2, 3, 4, 5, where it's almost trying to characterize exactly what's going on in the process as far as are there any type of thermals going on. Is because it's at the beginning of the pipe, it's this temperature. What's the temperature at the end of the pipe? Really trying to get tighter and tighter control of that temperature. And in the pharma industry in particular, I think we found finding ways to get a more accurate measurement, where it used to be half a degree C. Now they're looking to get better than half a degree C. So that's kind of some of the things that we're seeing on a day-to-day basis.
Yeah, I don't see anything that's going to replace the platinum resistance thermometer or a thermocouple anytime soon. So.
Okay, and one other question here. Can you recommend any solutions for induced noise in the feedback signal for RTDs, i.e. motor winding RTDs for motors using a variable frequency drive?
Yeah, it's just going to be, I guess there's no real good solution for that. Shielded cable is about really all you can do there. Really not any other way to look at that, at least that I know of.
Okay. Well, it looks like that's most of our questions. If you've got a question or you've got an application that you want to talk to us about, you didn't want to share it with everyone, but you got a question, we're more than happy to try to answer your questions, give you some feedback, and see if we can't get you pointed in the right direction. So certainly, send us an email directly or give us a call, and we'll try to get you your answer. So that our time is up for today. So we want to thank you for joining us, and we want to invite you to future sessions. We've got quite a few coming up over the next several months. So we hope to see you at a future session. And with that, enjoy your day, and if you happen to be in a cold climate, try to stay warm. Minnesota has finally warmed up, so we're looking forward to spring finally arriving. With that, we'll see you next time. Have a great day.